Hello, my name is Cameron MacKenzie, and I'm going to explain my research on analyzing the consequences of closing an inland waterway port. I am currently a PhD student in the School of Industrial Engineering at the University of Oklahoma. Previously, I earned a master's degree in Management Science and Engineering at Stanford University, where I specialized in decision and risk analysis. Here at Oklahoma, under the supervision of Dr. Cash Barker, I've been analyzing the economic consequences of closing an inland waterway port. We use simulation to analyze how companies might react to a port closure and then integrate these decisions with a multi-regional interdependency model. Waterway ports are an important component of the United States transportation infrastructure. Because of the importance of ports to both international and domestic commerce, there has been a lot of concern and studies on the risks that ports face. Events like a fire, a bomb exploding, a hurricane, a tsunami, or an earthquake could close a port and disrupt the flow of goods into and out of that port for several weeks or even months. Because these disruptions could be quite large, it is useful to study how the economy would be impacted if a port were closed. Our research makes several important contributions to existing port studies. First, our integrated risk model measures the effects of industry decisions following a transportation disruption. We do this by creating a simulation that incorporates industry tolerance for the risk of delivering products late when a disruptive event suddenly closes a port. Another important contribution is that our research focuses on inland waterway ports. Most research on port security concentrates on coastal ports, but inland ports face many of the same risks as coastal ports and should not be ignored. Finally, we apply this simulation and model to a port in Oklahoma. We use data from publicly available databases to generate realistic results for this case study. Results from our case study reveal insights into engineering and infrastructure problems that can benefit inland port decision-making. My presentation discusses the simulation, the input-output model, and the case study. In the simulation, a disruptive event suddenly closes an inland port. Because the length of the time that the port will be closed is unknown, each company follows a Bayesian updating rule to create a probability distribution over when the port will reopen. For each day that the port is closed, a company who plans to use the now closed port will have to decide whether to ship its product via an alternate mode, such as by train or truck, or wait for the port to open. As you will see in the case study, the biggest driver on whether or not a company decides to transport its product via an alternate mode is whether or not the company is monetarily penalized if its product sits at the port. If the company chooses to ship via an alternate mode, we assume the product reaches the customer on time and there are no adverse economic effects. However, if the company chooses to wait until the port reopens, its actions can affect other industries and cause production losses. We use the multi-regional dynamic inoperability input-output model, or the DIIM, to quantify these economic impacts. The vector Q here is a measure of inoperability for each industry. If a company chooses to wait to transport its commodities until the port opens, industries that were expecting to receive these commodities suffer supply shortages and consequently experience inoperability. The vector C star represents a reduction in final demand for each industry. If a company chooses to wait to ship its product, there is a reduction in demand for the industry to which that company belongs. This demand reduction is incorporated into the vector C star. If one industry is inoperable, the A star matrix calculates how other industries become inoperable because of the interdependencies among these industries. The T star matrix describes how the same industries in different regions are interdependent. The final parameter is K. We develop a new interpretation for K where K describes how quickly the inoperabilities and demand perturbations reverberate through the economy. We use the inoperability, that is the Q vector, to calculate total production losses. Let me now turn to how we deployed this model to the port of Catoosa near Tulsa in northeastern Oklahoma. The port of Catoosa is on the Arkansas River, which flows into the Mississippi River. The port serves as a transportation hub for Oklahoma and several surrounding states. 3 different rail lines move through Catoosa, and roughly 500 to 1,000 trucks come into and out of the port on a daily basis. Approximately $940 million worth of cargo came through Catoosa in 2007. Let's look at some simulation results now. In this simulation run, there is no penalty charged for companies not shipping their products. Companies have the option of transporting their product by train instead of waiting for the port of Catoosa to open, but without a penalty, there is no incentive for them to use the more expensive train. All of them choose to let their products sit at the port until the port reopens. In this simulation, the port is closed for 1 to 2 months. As you can see from the table on the left, on average, $111 million worth of product sits at Catoosa while the port is closed. This $111 million of unshipped product translates into total production losses of $6.2 billion for the 10 states that use Catoosa. In other words, the multi-regional DIIM translates the initial effects of the port being closed into 50 times the amount of the initial effects. Our next set of results shows what happens when companies are required to pay a 0.2% penalty on the value of their product for every day that their product is not shipped. In this situation, companies are highly incentivized to move their products by train. Only $11 million worth of product is not transported by train. The simulation reveals that companies are always choosing to use a train to transport their product unless they expect the port to reopen in the next 5 or 6 days. As before, the multi-regional DIIM translates the $11 million in direct effects to $663 million of lost production. Although large, these production losses are only 10% of the production losses when there was no penalty. This chart shows explicitly how the penalty affects industry behavior and production losses. The y-axis is on a logarithmic scale. The curve on the bottom shows the extra transportation costs that companies pay to transport their product via rail rather than via water. Notice that as the penalty increases from no penalty to 0.2%, the extra transportation cost only rises to $1.5 million. However, the average production losses for the entire region, and for Oklahoma specifically, fall from billions of dollars to hundreds of millions of dollars. More than $1 billion in production losses are avoided by spending less than $2 million. Our research here has demonstrated how combining simulation with the multi-regional DIIM can deliver a more nuanced picture of the consequences of a transportation disruption. Our simulation of industry tolerance for the risk of delivering products late can help us forecast to what extent companies would use alternate modes of transportation. The case study of Catoosa shows how important it is for companies to move their commodities by other modes rather than wait for the port to open. Our results suggest that if the port of Catoosa is closed and commodities are just sitting at the port, government officials may want to incentivize companies to move their commodities by other modes so that the region would avoid large production losses. Thank you for taking the time to watch this video, and I look forward to talking more about my model and sharing more of my results at the SRA annual meeting in December. See you in Salt Lake City.